Dr. Andrew White is our next speaker. He is an associate professor at the University of Rochester in chemical engineering with affiliate appointments in chemistry, biophysics, material science, and data science. He has a PhD in chemical engineering from the University of Washington, in addition to his postdoc training in chemistry at the University of Chicago. Andrew's lab studies deep learning and molecular simulation applied to peptides and small molecules. He and his group work on the adaptation of deep learning to chemistry and materials with a focus on graph neural networks, explaining deep learning models, large language models, and Bayesian optimization. Andrew has won Young Investigator Awards from NSF and NIH, Professional Society Awards in Chemical Engineering, Teaching Awards from the University of Rochester, and Engineer of the Year in Rochester, New York. And with that, I turn it over to you, Andrew.
Thank you. Yeah, this is a really interesting time. So I'm halfway between research projects, halfway between where I live, and halfway between institutions. So my talk is going to be a little bit disjointed, but hopefully it'll get you all excited about what's going on in the large language model community. So I'm going to click. Great. So first of all, a lot of the work I'm going to describe today is coming from my students, of course. So Gimi, who's now doing a postdoc at EPFL, did a lot of the explainable AI work. Sam, who is now out in San Francisco with me at our new institute, did the ChemCore project, which I'll describe a little bit. Murad is actually in Toronto right now, and everyone's off doing their own little things. It's really exciting as a PI. I do want to mention that I wrote a book. It's like, I don't know, like maybe 11 months old, so it's probably out of date, but it's called Deep Learning for Molecules and Materials. And it's like an introduction to deep learning if you know chemistry, because like I know there's a lot of introductions to chemistry. Well, there's a lot of introductions to deep learning, and I would send my students to that class, and they would come back ready to like analyze audio signals or images, and yeah. And so I got this. I wrote this book as like a graph-first book. But now I'm going to disprove deep learning, okay? So, all right, what is a molecule, okay? So this is something which bothered me for a long time in deep learning. And it's like a lot of the chapters in my deep learning textbook were about this. And there was this like really beautiful idea, this framework, which I think was a really powerful framework called an inductive bias. And this was how like I would organize in my brain, and many people still organize their thoughts on neural networks in chemistry with this idea. And it's like there's some fancy words for it, but basically it's how we build the neural network to reflect what we know about the problem. So like, do we know that we need to be rotationally invariant? Do we know that we need to have molecules coming in, right? This is what we work on here. So a lot of this is tied up in the representation. So when you basically start with a molecular graph, you're implying some exchangeability, symmetry, equivariance, invariance, depends on who you ask or what your math background is. But basically, if you swap the atoms that are equivalent, there should be no change in your output. That would be invariance. The equivariance is like if I'm predicting partial charge at every atom and I change the order of the atoms coming in, then the order of the partial charges should also swap. Very simple. My 2-year-old gets it, I think, but it's not that hard. Okay. But there's like this problem, right? Like that's how it all made sense, okay? Like you're like, okay, I want to work with the SMILES, I grab the RNN or the VIE. If I want to work with point clouds, I grab the equivariant neural network, right? And this brings us to the workhorse. I think if anybody is starting a project right now and you want to predict molecular properties, you should use a pre-trained graph neural network. This is the bread and butter, okay? I made this animation. It took a long time to make it, but I don't have time to talk through it, so let's just take a second. Okay, great. All right. But then those darn chemists, right? They came up with this thing called stereochemistry. And I think this is like the exact same talk that you gave, Georg, but it's, yeah, more jokes or something. But there's this molecule, and it's got like these, these two forms, right? And we like draw these little wedges here. There's a professor, actually, Connor Coley, I don't think he's here today, but he's like, okay, well, why don't we just put, a special character, instead of calling it N, we'll call it N, but with a stereo center. Sorry, not N, C. And so we thought we'd cracked stereochemistry, but then there's this other problem. This is called the Weisfelder-Lehmann test. So these are two molecules, decaline and bicyclopentyl, I think. And if you color their edges, this is crazy, okay? If you look at the red one here, it's connected to two greens and a red. The red one here is connected to 2 greens and a red. And if you will go take your graph neural network and you use it on these molecules, you will get the exact same properties. But we know that they're different molecules, different synthesis, different properties, but they look the same to a graph neural network. So a molecule is not a graph, right? So shoot, okay, fine. We can maybe fix that. There's these things called simplicial complexes, and you can get around it. But then there's this thing, these helical molecules. They actually don't have, they have stereochemistry because of the turn, can be clockwise or counterclockwise, but they don't have a stereo center. You can't isolate where that stereochemistry lies. You can't do it. So then you have to do equivariant neural networks. And Hannes is here, like, people who work on this, they're heroes. This is really hard stuff, okay? I'm just gonna skip over it. There's like, this is body order here. And there's like these tensors. I spent probably 3 months of my life learning about, what's this called? Representation theory. That is really hard stuff, okay? And then you go back to that picture and it becomes more complicated, right? And yeah, and then there's like these papers. This paper is incredible. Like it tries to break up you have exchangeability of the atoms, you have rotation, these spherical harmonics, you have these body orders, and it's all very complicated. Nobody's sure what the right answer is. But then, we're just getting started, right? If you think of the ladder of representations, we have descriptors, right? Then we had smiles, right? People got sick of trying to choose the right descriptors, so let's just use the smiles. And then people were like, well, smiles is not right, it's a graph, right? And then we got to the simplicial complexes to deal with the Weisfeller-Lehman test. Then we have nuclear coordinates, and okay, the computer scientists in the room, get ready, okay? Then there's conformational ensembles. I didn't make this, I made this a week ago, right? This is crazy. And then there's electron density, and there's even more. There's this thing called electron-electron correlation. Okay, but it doesn't matter, all right? So that's the question, right? We can go so deep. We can learn really complicated mathematics. There's a great paper, I think Frank Noe had one, and DeepMind did on a complete Monte Carlo simulation of electron density in a molecule, right? So we'll get there eventually. If you look at AlphaFold had equivariance in it, well, invariance. So they put an invariant point attention module in it, and it was hard, it was difficult. I couldn't do it. And they took it out, and this is how much it affected their accuracy. It went down almost nothing, right? So they went through all of the effort to put the invariant point attention module in. They took it out, it didn't do anything, but it takes up, maybe a third of their slides when they show the architecture. So, it doesn't matter. Okay, so I just got an iPad. Okay, no, this is an old slide. I've been telling myself to update the slide for a year, okay? I swear that I couldn't see very well. I was getting used to the iPad, the handwriting, it's gonna get better, okay? So here's my idea, okay? I'm gonna crack molecular representation right now, okay? Oops, no, I'm just gonna skip the slide instead. Okay, there's what we measure in the lab, the properties, okay? Then there's how we make things. And what's in the middle, the structure, it's just a shared hallucination, okay? There is no such thing as a chemical bond. You might laugh. Go read a paper on what is a chemical bond. There's a guy who spent 25 years of his life writing 5 papers maybe, on what is the definition of a chemical bond. And I don't think anybody else understands it except for him. There is no quantum mechanical observable for a chemical bond. Right? You think you know what a chemical bond is? Go look at cisplatin. It's a real drug, right? Where's the bonds? Doesn't make any sense. So here's my argument. And this argument was hard to prove in the past. My argument is that why don't we try to use what we can control, the synthesis, or what you order, the name of the molecule, that's what we can control. All this other stuff about correlations of the electrons, the conformational ensemble, that's all just, it's make-believe. And then you have what you measure in the lab, right? Okay, so here we go. So that was a hypothesis of mine. And then there are these papers, and it's just not just me. Kevin Jablonka, Baron Smit did a paper on this, and then Pale Das has this paper, which I don't know if I believe it, on model reprogramming, where they basically take an English language model and make it make antibodies without any extra work. It's crazy stuff. If you take this sentence, the solubility of 1 gram of propane is, and then you don't fill it in, you ask the language model to fill it in, you get a solubility predictor that gets an MAE of 0.5. Okay, so I don't know if anybody's ever done solubility prediction. It's really hard. Okay, so getting a correlation coefficient of 0.92 in your solubility, that's really impressive actually. Okay, so we can actually now predict solubility by just going to a large language model and putting in an English language sentence. And I'm hiding some details here, and I'm happy to talk more about it. But there's basically some tricks you can do where you can get uncertainty, and we even do Bayesian optimization with this, okay? So we get uncertainty, it's instant, it's great, right? Now, but here's the idea, is that you can actually go even farther. And now I'm free to use natural language, right? I can represent lots of things in natural language. Here is me writing out a reaction by writing down the catalyst processing and synthesis, the reaction conditions, and then like the contact time, and then I predict the yield. And I can train these language models to predict the yield. So this case, we got the best one was like a 0.82 correlation coefficient for yield. And this is oxidative coupling. And this is, it's incredible, right? Like if I were to try to do this before, I would have to decide what are the features for my catalyst, what are the encoder for my molecule, how do I represent flow rate? And here I just put a paragraph of text in. Okay, so my life has been on fire the last 6 months because this is just crazy, right? Like this is just, some things weren't impossible now. And so we have a hypothesis that natural language it should be the default representation. There are times when you need to have per atom representation, but I believe we can go very far with natural language, okay? But then can it be the output, right? So this is a really cool project and I would love to talk about it, but I'm almost out of time. But we did a lot of work on doing explainable AI and having the explanation be in language, okay? So we have a model that predicts solubility again, and it gives you a paragraph of text. The presence of a carboxylic acid in the heteroaromatic group, and this molecule are both positively correlated with this aqueous solubility. The carboxylic acid group is especially important as it's highly polar and can form hydrogen bonds in water. Okay, this is a model. It's a black box model. We don't need to know what the underlying like predictive model is. This works on any prediction technique, and it gives you a paragraph of text. How do we do this? We did QSAR, right? We did QSAR. It's like this is the traditional method, but we have to make a QSAR model that only works around one molecule. So each time we have a new prediction, we make a new QSAR model, and then what's great about these QSAR models, and you don't know which features are important, you can actually have a large language model, look through the QSAR, and turn it into a coherent explanation. Cool, so now natural language can be the input, natural language can be the output, but what else do we need to do? I have no idea how much time I have because we started late. That's okay, don't worry about it. Okay, so now, okay, we're fine, we're in good shape. We know now that natural language just solves all the problems, and we asked ChatGPT, how many alcohols are in this molecule, okay? Now, you take a minute here. There are 2 alcohols in the molecule, all right. So I think that's wrong, all right? So, and that's right, like GPT-4, it can't count the number of letters and words. It can't count the number of alcohols. If you try to do synthesis, it doesn't work, right? So how do we reconcile the fact that we can get really far with language in some cases, but other cases we can't? Like we can't multiply 2 6-digit numbers with LLMs. Well, it's just like how I can't multiply 6-digit numbers in my head. I can't count the number of alcohol groups in an organic molecule. But what we can do is we can give these LLMs tools to ease the things that they have trouble with. Okay, and this is this idea of like agents. So now what we're going to do is we believe that we can use language for the machine learning part. We believe we can get language out from the explainable AI part, but there's a lot of chemistry that we don't need machine learning for, right? We don't need a machine learning method to count the number of alcohol groups in a molecule, right? Or we don't need machine learning to do retrosynthesis in general. Like a lot of it is, well, maybe you do, I don't know. But a lot of things we don't actually need machine learning for. And so I'm going to just go quickly here. Basically, we wrote a paper, and it came out, a little while ago. You can read through it, and basically, we show that if you compare like an expert PhD student choosing computational chemistry methods, and then you have these models, do it, the models beat the students most of the time, and they get like 75% accuracy on anything we throw at it. These are like, I'll give you an example. Like one of them is like simulate the hydrogen atom spectrum using whatever packages you need, and it can go and get these things. So it's really remarkable what can be done. I'm going to skip over this here, but basically then what we have done is we take these models which can write code, use tools that exist, like they use PySCF, they can use RDKit, and then we put them all together into an agent, and then we give the agent high-level instructions. So design a compound with the same mechanisms to dasatinib and purchase it. And then what can happen is it goes through these processes. It can actually use the tools. So I'm not going to, again, I don't have any time, but so like it has a thought, I need to find some compounds with the same mechanism, so then it reads papers. Reading papers is a tool that it has, right? It works in language. We write papers in language, so it can read papers in language. So it finds some molecules. And then it needs to get the smile strings. Now remember, it's not good at tasks like counting letters or anything like that, so it doesn't know the smile strings of a molecule, but we can just give it access to PubChem or something. So it can turn these names of molecules into smile strings, then it knows how to modify them. There's lots of existing deep learning tools for modifying molecules. Then it checks, if it can purchase it. So it looks in a database to see, can I purchase this compound? And then it makes an order form. It even can write an email, all right? And then we put it together with a robot, okay? So it's like, okay, we can do all these tools. Let's actually try to make it real. Okay, I have like 2 minutes left. Yeah, it's fine. Okay, so great. So then we said, make an insecticide. It made an insecticide. Like it looked up what an insecticide is, came up with a synthesis route. It went and it made the matter, and it came out, out the robot. Then we did, here's an example. Like to synthesize a molecule similar to paracetamol that doesn't contain a methylamide group, then find the price of this molecule. If it's above $500, plan a synthetic route. It does all these steps to complete this. Here's one, we asked it to make a novel dye, like make me a new molecule that's never been made before with a specific wavelength of light absorption. Makes a machine learning model to predict the absorption of light, proposes a synthesis route, a 2-step route, looks up this molecule, it's never been made before, and it makes it on the robot. And it is like 15 nanometers off. All right, so, okay, great, it works well, it works great. ML is now a core tool for drug discovery, no company's ignoring it, but I think it's been an evolution, not a disruption yet, okay? And I think that if we can start to automate at this scale, where every time a new tool is made, or every time a new breakthrough comes, and we can start composing them together with all of the papers that we've written for 350 years, I think that is going to be the disruption in drug discovery. All right, the end, okay.
Andrew, that was really cool. So we use my lab. We use language models and we design proteins. They work in the lab. It's really kind of corroborate this. But I guess you kind of made a jump, right? You went from really core structural modules all the way to natural language. But what about the intermediate, which would be say like a chemical language model or a protein language model? Why? Where do you feel like those fit into this thing? And if would those inform the latent spaces of the natural language models to do better synthesis or generation?
Yeah, I have this idea that I need to build like an AI scientist one piece at a time. And what you're talking about is giving it eyes. Like right now it can't see the molecules. All it can do is write RDKit code to like count the hydrogens, right? Or it can write, maybe it can write some XAI stuff. What's the solubility, and give some explanation of why it's got the solubility. But what you really need to do is give it vision of molecules. So yeah, that's the next step, is to let it actually see what it's designing. We're not there yet, but I'm sure it's just a matter of compute. There's nothing fundamentally in the way.
So how do you know that your models aren't just a fancy table lookup?
Well, I mean, we judge these things based on,
right?
That, but we evaluate them like they're a chemist. Does it come out? Does it have the wavelength right? Does it come out of the robot? So I don't care if it's a table lookup.
But if it's not a table lookup, it may not get you to something novel. So I can see where you can get a solubility model where your language model just went and looked, and somewhere on the internet it had the solubility for that molecule and it plugs it in. But that's not useful.
Well, I think this is a composition of machine learning tools. So yes, if machine learning tools cannot extrapolate, then we're dead. I believe, and I think many people in this room believe, that machine learning models can generalize to new compounds.
I agree. I just don't know if a language model approach like what you have is going to generalize.
Well, so we're not actually using, the language model never touches the chemicals in general. Like in my last part, you're right. At the earlier part where we did solubility, yes, yeah. You're right. That's true. And what we did there is we didn't actually do solubility because we don't really care as much about solubility. We did novel catalysts. And I don't have the slide. I'm happy to show the slide. It's in my talk normally. We went into the lab and we built new catalysts by cutting out, we restricted the catalyst space. We only wanted to use really cheap catalysts. And we actually went and prospectively designed 6 catalysts in a row sequentially, and we got within 2 points of the thermodynamic maximum of the reaction. So you're right, a lot of this stuff is crazy, and we should make sure it works. And I wouldn't talk about it unless Kevin, and Baron had the same result, and the Pale had the same result. And we haven't submitted this paper to a journal yet until we get another second system. It could be a fluke retrospectively. It maybe just work once prospectively. We're going to try it a third time, and then I think if it works, that's remarkable.
Cool, thanks.
There is a recent endeavor to integrate Mathematica with large language model. So how about integrate first principle based and large language model based predictions? What is the balance?
Yeah, I think in 2021, in the summer, I was with Glenn Hockey from NYU. We were sitting in his office, and I said, no, it was a pandemic. I was on Zoom in his office, and I said, you know, let's try asking this LLM plot the H2 dissociation curve. And so we put in the sentence, plot the H2 dissociation curve, and it went and it imported this Python library, which I didn't know at the time, called PySCF, which is a Python like quantum chemistry library. And it set up the system, ran Hartree-Fock at different spacing, and made a plot with the axes labeled almost correctly. And so, yeah, I think there's not that much distance from that. This is like 2 years ago. I haven't tried it again. I mean, it was so close I didn't ever try it again. But I'm pretty sure you can already use Gaussian, PySCF. You know, we actually wrote a paper on it, can write Gaussian input files. I don't have a, and what's the other one? No, Gaussian, yeah, I don't have a license for Gaussian. So I'll send you the files if you have a license. But yeah, it seemed to work.